In this video, we are going to continue going through probabilities, and we're going to do that by looking at what's known as a joint distribution table. Actually, I'm going to go ahead and make sure that I'm out of the way so you guys can copy this down. So make sure you get this table down. This is just an example, but we're going to be using this. But I'm going to have to erase it for us to actually be able to use it. So make sure you get this down. So anyways, as y'all are doing that, a joint distribution table, it's essentially a frequency distribution, but instead of only having one variable, we have two, right? So here we've got, along the top, we've got different types of vehicles, right? Along the side, we have different colors. So this is going to be kind of our little joint distribution table for kind of vehicle type and color. All right, so we are going to use these to help calculate probabilities. So the way these work, in case it's probably pretty self-explanatory, but each of these cells, right, it tells us how many observations of a specific type there are. Right, so say this middle one, right, that's lines up with blue and truck. So this is telling us there are 45 blue trucks in our kind of data set. So on and so forth, right? So here in the bottom corner here, this is, there are 17 green sedans, right? So on and so forth. That is how we are going to use this. All right, now when you first get one of these, probably one of the a smart thing to do is to add up all of the rows and all of the columns. Right, one, that's going to just give you the overall row, and even if you don't end up using it, it can be faster to just get them all done all at once, so that way when you do need one, you don't have to stop and add the row up. Not that it's that big of a deal, but I always prefer to do it that way, but it's really going to be up to you. All right, so as we look at these, if we were to add up these rows and columns, I'm just going to go ahead and put those numbers down just so we can go ahead and get to the examples. All right, so once you add up either all of the rows or all of the columns, you can also stop and add those up, and that's going to give you your total number of observations. All right, what you don't want to do is add up all your rows and add up all your columns and then add all of the numbers together, right? Because you're going to double count everything and all of your probabilities are going to be half as large as they should be, right? So you only want to get kind of one group, right? So either kind of this side at the far edge or down here at the bottom. Don't add both up. All right, but for us, I'll go ahead and just write this over here. All right, down here in the very bottom corner, whiteboard's coming apart. Anyways, our total number of observations is 258. All right, but I'll go ahead and finish writing these out. All right, and there we have it. All right, so when we first get one of these, all right, if we're looking at one of these, this is something we might want to do right off the bat. It can be helpful. It can save you some time later on, but again, it's not necessarily mandatory. All right, so if you haven't gotten this copied down yet, you might want to just go ahead and pause the video and finish copying it down, because I'm about to erase it so we can look at some examples, right? You also want to keep this where you can see it, what am I looking for? Oh, that's what it is. So that, you can actually see, hey, what's being referenced. All right, I'll try to be as explicit as possible when talking about where we're grabbing stuff from. All right, so we've got a couple of different examples that we're going to do, and we're just going to kind of run through these. We're not going to do anything super fancy, but just kind of look at how to use this joint distribution table, and then also just get more practice with some of these probabilities. All right, so let's start with just a relatively easy one. Let's just start with a simple probability about one event. All right, so not a compound event, nothing like that. We're just going to ask, what is the probability of seeing a red vehicle? All right, so P, open bracket, red, or open parentheses, red, close parentheses. All right, what does that equal? How are we going to figure that out? All right, so if we're just going to use that classical approach, we're going to look and say, well, how many observations are in red, right? How many observations are in my event, right? So we can, if we already did the adding up of that row, we can see that there are 97 red cars, right? So we get this by just looking at that top row of the joint distribution table, right? Getting the red SUVs, red trucks, and red sedans, adding those together, and we'll see that there are 97 of those. All right, then we divide by the total number of outcomes, which is 258, and we'll see that 97 divided by 258 is 0.376. All right, and that would be our answer. All right, so that's what we're looking at there. All right, so now let's move on to something slightly more. Well, actually, let's do this one. Y'all don't know what order I was going to do these in, so it doesn't really matter. I can change that as much as I want, but let's do this. All right, so let's say I want to know what is the probability that you see a green truck? All right, if I ask that, then hopefully we should know that we're talking about an intersection, right? Because a green truck would have to be a truck that is both green and a truck, right? So green and truck, right? That's an intersection, right? So here we just look on our chart, right? We're going to find truck in the middle, green at the bottom, all right? And so the kind of middle row, middle column, bottom row, we're going to see the intersection of truck and green, and that's going to be 29. All right, so there are 29 green trucks, right? And this is out of the entire sample, right? The entire sample space. So 29 divided by 258, that is going to give us a probability of 0.112. Right, next we'll do what's the probability of seeing a SUV, a truck, or both? All right, so in this case, right, that or both is a dead giveaway. That tells us that we are going to be calculating a union. All right, so what's the probability of the union of SUV and truck? Right. The next thing that we need to do once we know that we're looking at a union is we need to ask ourselves, are these events mutually exclusive? Right. So we know that if they're mutually exclusive, then they share no common points. Right. So we can just go and look at our joint distribution table. Right. Are there any places where truck and SUV cross over? Right. The answer is no. Right. Which also makes sense because they're the same. They're part of the same variable kind of type of car, so you wouldn't expect those to be, you would expect them to be mutually exclusive. All right, but these are mutually exclusive, so that means that we're going to use the sixth law of probability to actually calculate that probability. All right, so probability of SUV plus the probability of truck. That's how we're going to find the probability of this union. All right, so we just go, again, looking at our joint distribution table, we see the column with SUV. If we add that up, we're going to get 75. So 75 over 258, because that has not changed. All right, then we look and see how many trucks we have, 111. All right, divide that over 258 as well. When we put that all together, we're going to get a final probability of 0.721. All right, so let's move on. All right, so what if the next time, all right, or this time I should say, we're about to do it, I ask what's the probability of seeing a vehicle that is red, a sedan, or both? All right, so what's the probability of seeing a red vehicle, a sedan, or a red sedan? All right, so once again, this, that or both, that's telling us that this is a union, and that's not how you would write sedan. All right, so once again, all right, we know that that is a union. We need to ask ourselves, are these events mutually exclusive? All right, so we can go to our joint distribution table and we can look and we can see that there is a place where the row with red and the column with sedan intersect, right? So they are not mutually exclusive, all right? So we cannot use the kind of formula for the from the 6th law. Instead, we're going to have to use the 8th. All right, so we're going to have to find the probability of red, add to it the probability of sedan, and then subtract the probability of red sedans. All right, so red we've already done. That was 97 over 258. All right, then we're going to add to that the probability of a sedan, which is 72 over 258. And then we're going to subtract the intersection. All right, and so there are 32 red sedans, 32 over 258. I'd like to take this this time just to kind of go back over something we went over in a previous video. All right, so why are we subtracting this intersection when we're doing these kinds of probability of a union calculations? All right, well, when we added up the row with red, all right, we included those 32 sedans, and when we added up the column for sedan, we also included those 32 red sedans. All right, so those 32 red sedans are incorporated in both the 96 and the 72. All right, and so we are counting altogether 64 red sedans, even though that there are only 32. All right, so we have to remove one of those observations, right? So you can think of it as we're taking it out of this 97 or we're taking it out of the 72. Doesn't really matter, especially since that's not necessarily what we're actually doing. All right, but all right, we've got to pull that out. All right, but once we plug all of that into our calculator and hit enter, we're going to find that we have a probability of 0.531. All right, for this next one, I'm going to go ahead and erase this. So this next one is going to be a conditional probability. All right, so we're going to say, what is the probability of seeing a sedan given that it is blue? All right, so the probability of sedan given blue. All right, I think this is where the joint distribution table is really helpful because if you recall when we were talking about conditional probabilities in the last video, I mentioned that what we're doing essentially is just shrinking the sample space. All right, that's really easy to do with our joint distribution table. Right, so we can look at it and we can say, well, we're only looking at the blue. All right, so we know that the vehicle, whatever it was blue, right? And so we can forget about all the other vehicles. We just want to look at the blue ones. All right, so our denominator would be 82, all right, because there are 82 blue cars. All right, then if we want to know the probability that we saw a sedan out of those 82 cars, right, well, we just need to find how many of those blue cars are sedans. So we just look for the intersection of blue and sedan. All right, we find that there are 23 blue sedans, all right, and that the probability is 0.280. All right, so using these joint distribution tables, in my opinion, makes calculating these conditional probabilities so much easier. Right now, if you don't like this method and you want to do 23 over 258 divided by 82 over 258, which would be the kind of more traditional probability of the intersection divided by the probability of what's given, then that's fine, right? There are multiple ways to do a lot of these problems as long as you come to the right answer using a consistent method, right? That's fine. All right, so that is our conditional probability for sedan given blue. Now I'm going to ask a question. Are sedan and blue independent? All right, so we're going to look and see if a vehicle being a sedan and it being blue are independent of one another. All right, so probably the first thing we would do is, since we've already got the probability of sedan given blue, we would just look for the probability of sedan. All right, and so again, this one's going to be relatively straightforward. There are 72 sedans out of 258 vehicles, and that gives us a probability of 0.279. All right, so as I was doing this example and writing it up, I saw that these answers are really close. All right, however, they are not equal to one another. Right? They're off by a very small amount. So if you had a question on a homework or a test asking you if sedan and blue were independent, then after this you could say no. Right? The answer is no. These are not independent. They don't, seem to have much of a relationship, but they do have. It is present there. Right? Those numbers do not equal one another. Right? And in fact, actually, if you'd, they're very close to being independent, even though they're not. If you do the other set, you'll see that they are also kind of within 1/1000th away of being the same number as well. Right? So these two, very, very little kind of effect on each other, right? But not independent, right? So again, this probability of the sedan given blue would have to equal the probability of sedan for it to be independent, right? It does not. So these are not independent of one another. All right, I think that is it. Yes. All right. So that's it for those joint distribution tables. I'll go ahead and tell you that I really like the joint distribution table. I think it's one of the better ways to give y'all this information and then run through some probabilities. So you can definitely expect to see these on homeworks and tests. All right. But that's it for this. In the next video, we will wrap up Chapter 5, and we will be looking at counting rules, all right, which is probably just as exciting as it sounds, all right? But that is what we're going to be doing in that video, and I will see you then.